Okay, so can any one of you confirm me that you are seeing my slide and I am audible? Just write in chat box once. Okay, thank you, Sunil. So yeah, so let me start now. So good evening all, and welcome to the NPTEL online certificate course. Its name is Analytical Chemistry. This course is taken by Professor Devasis Ray and myself Satya Prakash Yadav, a PMRF scholar from August 2020 batch to present. I am working with Professor Satish Patil in SSU department, Indian Institute of Science, Bangalore. So about this course, so it's a 12-week course. So we are in the 8th week now. So in the first week, we have discussed about chemical and material analysis method. In week 2, we have seen what is the role of analytical chemistry and their technique. And then we have in week 3, we have discussed the chemical equilibria and what is the basis of chemical equilibria and the chemical analysis. And then in the week from week 4 to week 6, basically we have discussed about spectroscopic method. Here we have discussed UV, IR, fluorescence. And in week 7, so last week, we have mm, discussed about the thermogravimetric analysis. And in the sorry, so this week we are going to discuss about the DTA and DSC mostly. So if you have gone through the lecture in week 8, so in the week, uh, sorry, this lecture is 36, this is 37, 38, this is 39, this is 40. Sorry, I haven't changed. So this one. So what in all we have read in the lecture 36. So in the lecture number 36, so basically we have seen the sample control TGA and what are the different types of crucible. So what do I mean by sample control TGA? Means how the amount of sample uh, can help you to get a proper TG curve. So like suppose if we are seeing the faster change in mass, so we have to slow the heating rate. If we are seeing the smaller change in mass, we have to faster the heating rate, like that. And in this lecture, basically we have discussed about different types of crucible, like alumina crucible. What are the advantage of alumina crucible? What are the disadvantage that lead to us to sapphire crucible? And what is the disadvantage of this sapphire crucible to that leads to a platinum crucible? And what are the like a drawback of platinum crucible? So in this lecture, basically we have seen about these things. Now, in another thing is that we have seen the interpreting the TGA curve. So, what are the different types of TGA curve we are seeing? Like, if we have, like, suppose thermal decomposition with the formation of volatile reaction product, if there is a corrosion or oxidation of metal, formation of volatile oxide, combustion of carbon black, or like in the environment of nitrogen 2O2, multi-step decomposition, explosive decomposition with recoil effect. So this kind of thing we have seen in the lecture number 36. In the lecture number 37, we have seen the TGA curve of copper sulfate into pentahydrate. So we have seen this TGA plot, DTG plot, and its use. And basically in this lecture, we have seen the introduction of DTA. So the question will come in the assignment. So what are the like how this copper sulfate uh, thermogravimetric curve looks like, and what are the different peaks, how we are going to assign, how we are saying that how the water molecule loses and what is the end product. And DTA will tell you the what is the exact temperature where process is happening. And then we, so in this lecture, we have already slightly introduced to the DTA. Okay, and in this also we have learn a process called caramelization. One question is also there in the assignment in this question. And in lecture number 36, basic 38, we have seen the what are the application of this DTA in the chemical reaction. In lecture number 39 and 40, these are interchanged. So in lecture number 39, we have seen about the DS, differential scanning calorimetry, and its instrument and their application. So in the 39, we have seen that why we went from DTA to DSA. So what is the important thing? Like if we are going to do the quantitative analysis, so that lead us to DSC. So types of DSC, what is the principle of operation of DSC, and we have seen the different types of processes happening, like large well-defined endotherm, shallow broad endotherm, and similarly for the exotherm also. So these things application we have seen about the DSC. And in lecture number 40, basically we have seen the about the DTA, because these got interchanged in the video lecture. So in principle, this should come first and this should come last, but somehow it got like misplaced. So their DTA, we have seen like what is the DTA curve, how we are going to assign the curve, and what is its application. So these things we have learned in the peak number 8. So if you have gone through the lecture from 36 to 40, so you have get an idea about these many concepts. Now coming to the this uh, question assignment 8, question number 1. So it's saying that in which method of analysis temperature change parameter is measured against temperature or time of a sample and a reference. So A is electroanalytical method, B is the DTA, C is the APXS, and D is the TP. So just write in the chat box what is the answer for the question number 1. So anyone can take the lead and write the answer for this question number 1. Okay, Sunil Pawar is saying B. Okay. Anyone else? Anyone else who has a different answer than B? Okay, so let me tell you in detail. So what is electroanalytical method? So in this, what we basically study the electrical property. Okay, so here we measure the electrical property in the electrical properties like voltage, current, etc. Right? In DTA, basically we have taken one like reference sample. We have one a reference sample and we have sample. We heat this sample. So if the TR means reference temperature is equal to TS, means there is no reaction is happening. If TR, if TS is greater than TR, what is happening means this sample is evaluating heat, means this is the exothermic reaction. Exothermic reaction, right? If TS is less than TR, what is happening means this heat is consumed. That's why the sample temperature is getting like a reaction is happening which is taking the heat from the sample. So this is the endothermic reaction. Endothermic reaction. So this is, here we plot delta T, which is Ts minus Tr with respect to your either temperature of furnace, or with the time, because here temperature is the linearly related to the time, so we can write it. So how the plot look like? So if we see the DTA plot, how it's look like. So suppose this, if there is no process is happening, so it will go. If something is happening, either that Ts minus Tr will go down, or another way it can go up or down. So this is your basically here Ts minus Tr is negative. So this is endothermic reaction, and this is the exothermic reaction. Exothermic reaction. Right, so these are the two kind of plot we will see in the later quiz. And this is the, in the first class I have told about, this is the um, alpha proton X-ray absorption, X-ray spectroscopy. So here we see that there are three types of processes happening: Rutherford backscattering process, proton emission process, and X-ray fluorescence. So with this, we like with the Rutherford backscattering, we find out the CNO. From the proton emission, we find out sodium, magnesium, aluminum, silicon, and sulfur. And for X-ray fluorescence, we determine from the sodium to iron. So these things I have already told in the lecture number 1. So if anyone interested, they can go. And TGA, we know that this is a thermogravimetric analysis. So here basically what we plot in the previous lecture, you can go ahead. We have this percentage mass, delta percentage mass change, right, versus temperature at time, right? So I think this will be clear why the question number, the answer number B is for the question number. Let me go to the question number 2. So in the thermogravimetric analysis of the iron powder in air, results increase in mass due to what? The formation of volatile species, or the formation of non-volatile iron oxide, decomposition of iron sulfide, or decomposition of the iron sulfide. So anyone can tell the answer for question number 2? Okay, so Neil Pawar is saying B. Anyone else? Then I will go and explain with the spectra and all. Anyone else? I will wait for some 15 more seconds. Okay. So basically Sunil Pawar is right. So this is the example of chemical reaction with increase in mass. So we have seen this in the lecture number 38, where like we have seen the chemical reaction with increase. So what happens? This, in presence of oxygen, this iron will form in presence of air, means here we have O2. So it will form this non-volatile and volatile iron oxide. Iron oxide. So basically two oxide is formed. This is a Fe2O3 and Fe3O4. Right. Now if we go by the answer, so first is the formation of the volatile species. So this is wrong. Why? Because if we are forming a volatile species, it will immediately go away from the your sample holder. So the mass will decrease here, right? So, but here we are interested in increase in the mass. That first is wrong. And the decomposition of iron sulfide. So here we have iron and we have only oxygen. So there is no way it can form iron sulfide or iron cyanide, whatever this is, iron cyanide, correct? Cyanide. So this is the two immediately, like um, uh, we can immediately eliminate these two options. Only the this formation of non-volatile oxide is the correct answer. Now this is the TGA plot for this one. So suppose the first thing is that they have taken this 23.7141 mg. Now we are seeing the 40% increase in the mass in this step. So that 40% is basically your oxygen which is taken. If you calculate this Fe3 and Fe2O3 and Fe3O4, this will change, the mass change will be 9.48x3 mg, correct? So this one I will calculate one for this copper sulfate pentahydrate, because I have to know the what is the molecular mass for iron like uh, Fe3O4 and Fe2O3. So here basically this is the spinel. So I will tell you one important thing about the Fe3O4. So this is a spinel which is Fe2O4. So here this has mixed valence oxide. So here it will be iron will be a 2 and in the iron 3. So this you have to find out what is this, whether it is inverse spinel or normal spinel. So we have to go to the find out the octahedral stabilization energy. From there we can find out whether it is spinel, normal spinel or inverse spinel. That is the one thing. This is the only iron 3 plus is there. And another thing, we have the synchronous DTA plot. So DTA, what it will tell, whether the like heat is evolving or heat is absorbed. So this is the exothermic reaction, because your sample temperature is increasing with respect to reference. So and the area under this peak will give you the enthalpy change. So this is all about in this uh, question. So in the question number 3, during the thermogravimetric analysis of sucrose at temperature more than 230 degree, the sucrose get molten. What is it called? It's called caramelization, galvanization, or polarization, or none of the above. Any one of you? Okay, Sunil Pawar is saying caramelization. Okay, anyone else who has a different answer than this? Okay, so Sunil Pawar is absolutely right. So I will just show you how this thermogravimetric analysis of sucrose look like, and then we will discuss. Sorry, just it got stuck. Okay, so this is the decomposition of sucrose at 10 Kelvin per minute in the air. So what is happening? This TGA. So now the TGA is initially it is a flat line, means up to 230 degree there is no decomposition. But what is happening? The mass is decreasing. Like so, this mass here it is written in the state there is a 31% mass loss, and it is this. So suppose you have taken in the initial. Okay, it's not written here. So how much sample you have taken and how much it is losing in the first step. This step, 67% of mass is going out. So the what is the caramelization? So I will just tell you. So uh, this caramelization of sucrose, basically this produce this large brown color. So these are brown color molecule with some small molecule like these are volatile, like suppose this is the furan, maltose, and diacetyl. So what happens in caramelization of sucrose? It's produced the large brown molecule which are caramelin, and caramelin, right? So these are the three compound which forms upon heating of the sucrose. So what happens? So basically, first we heat the sucrose. So here, what will have? Water molecule will go away, and it will form the monomer unit. So sucrose is made up of the alpha glucose and beta fructose. Now, what will happen? This glucose and fructose, they will algomerize and form a sticky compound. This is oligomer. Now, these fructose and sucrose, they can decompose also in the volatile substance like maltose, furan, and diacetyl, and other compound. And what happens? This sticky compound, this will lose the different number of water molecule and form the different types of compound. And these are the in the brown in color. So basically, if it is giving away 12 molecule of water, so it will form caramel. If it is removing this 18 molecule of water, it will form the caramel. And if it is giving 27 water molecule, this is a caramel. So these are the different molecule which form upon this decomposition of sucrose, right? So they are in the uh, brown in color. So what is happening? This is your process, right? So if we see the detail curve, so what is happening? Your first sucrose will melt here, and then this is the caramelization process, and it will keep on increasing. So this melting is endothermic process, but this caramelization is exothermic process. That's why your temperature will keep on rising up to 500 degrees. So these are the like this is saying that the endothermic melting peak followed by the endothermic caramelization at which stage that exothermic decomposition. After that, this exothermic decomposition or combustion. So this is the exothermic. These are the two endothermic peak. So these are all about we have to know in this question number 3. Correct? So what happens during the gravimetric analysis of sucrose if its more temperature is more than 239 degree? Right? Now I will go to the question number 4. So what is saying in thermogravimetric analysis of copper sulfate pentahydrate temperature more than 780 degree, what residue it happen? Can anyone write what residue it will form? And this has a very nice concept here that if anyone can write why they are particularly saying this is your answer, then then it will be good. So Sunil Pawar is saying A. Anyone else? Anyone else who has the different answer than this um, different answer that Sunil Pawar? Because this is the wrong answer. So I will open the spectra, sorry, and then I will ask once again. Oh, it is hanging. Give me 1 second. Okay. Now I have given you the spectra. Can you tell me now, like, what is the product which form upon this decomposition of CuSO4 pentahydrate more than 780 degree? Sunil, can you now correct your answer? Okay, you are saying B. Still you are wrong. That is the concept. If you get that concept, you will know what is the answer for this question. So it should have CuO, but there is a different species which farm at 780 degree. Now you have to tell me. Do you want to change your answer still? Okay. So let me tell you. So this both the answer are wrong, right? The actual answer is Cu2O, right? So here I will tell only what is the concept. So what happens here? Here you farm the CuO. Here you farm a CuO, but this is not the end product. This all the like steps I will explain in the other question. There are deep, like detailed question is there for this copper sulfate in the upcoming. So here I will tell why this Cu2 is the right answer. Sorry. So this CuO is not the end product. Why? Because this CuO is prone to reduce, right? So it self reduce into a Cu2O and half O2. So this is the concept here. How people have arrived that it will form the Cu2O, because once you calculate the mass, what is the initial mass and what is the final mass. From there, you will find out the final end product is not the CuO, it is the Cu2O. Why? Because the self reduction of CuO into the Cu2. So here it is in the +2 oxidation state, here it will be +1 oxidation state. Right? So this is your real end product. Okay. Other spectra I will explain in the further question. One detailed question is coming there. I will tell you all these things. Is it correct, Sunil? Can you please let me know that you have understood the concept why this Cu2O? Okay. Thank you. Now choose the correct option given below for the following statement. So DTA measures the temperature change over the time. TJ measure the mass change over the time. DSC measure the amount of heat, or all are the correct. Can you tell me? Okay, saying D, all of this correct. Okay, so basically you are right, because in DT I have told you this is the delta T versus TF, like furnace temperature, and we see this kind of plot. This is the your DTA. This is TF for time because linearly correlated. TJ we have the mass change, percentage mass change versus time or temperature. This is your TGA. DSC basically we measure the amount of heat, delta W, whatever you say, or delta Q versus time. So this is this. All the three are correct. So hence your answer is the right. So you are correct. Okay. Now next is the question. In the thermogravimetric analysis of copper sulfate pentahydrate, the step of decomposition of 5 water molecule in copper sulfate is. Can even tell like what is the answer for this? Question number 6. Okay, Sunil is saying C. 2 water molecule, then 1 water molecule, then SO2, and then 5 O2. Okay, yeah. Now can you tell me 0.5 O2 from where it is coming? Sunil, just I have explained, right? 0.5 O2 from where it is coming. Okay, so let me show you the spectra. now I will little bit go into this detail. Okay, here. So now, so first thing is that here they have taken the 10 mg of your sample. So this is the, like, sorry, they have taken somewhere 30 mg. I will just check. Yeah, they have taken 31.5 mg. It's written here. Here. Now I will go into detail how they are going to analyze. So, so first step, they have lose this 4.5296 milligram, which is your 40%, 40.34% mass loss. Now, if I ask you how you are saying that there is a two water molecule loss. Now we have copper sulfate pentahydrate. So this molecular weight, what is the molecular weight for this is your 249. These are taken from the like Google, or you can just add all the atomic weight and get it. So what is the molecular weight? Copper sulfate. Now if we decrease here, so the 31.1 milligram after decrease in the 14%, 14.4%, you are losing actually 4.52 gram. So first it measured that we have 13.5 mg. After that it has measured that it is not 13.5 mg, it is 31.5 minus 4.53 milligram. So whatever it is coming, that much milligram he has find out. Now he has to find out what is that 4.5 milligram. So the like 31.5 milligram, what is the X percent is your 4.53 milligram. So now here you can get what is X. So your X is 14.4%. So this way you can find out. So first weight you find out, what is the second weight you can find out, then difference will be 4.5 milligram. Now you have to calculate what is the percentage of 13.15 milligram. What is the percentage of 13.5 milligram, which is 4.53. Now here we find out that this is the 14.4% loss is there. Now we will, because it's a mole, so it equivalent to it will reflect in the molecular weight also. Now if we decrease this 14%, 14% of 2.4968, so 249.68 minus 249, 14%. So what it will be? So this is your the the unknown species molecular weight in the space step 1. So this will be, this if you calculate, it will come to 213.68, which is the molecular weight of copper sulfate into 3 water. So if you take the molecular weight of this will be your 213.68 milligram. So from here we can say that in the first step two water molecule is losing, and it is forming a copper sulfate into 3 water molecule. Now again it is more or less same mass loss, 4.47, which is 14%. So this 14% will again 2 water molecule it is losing. Then again it is 7.34%, 37%, which is half of this. So this is 1 water molecule, and then we are losing 32%. So now what is the molecular weight for the copper sulfate? We have to find out. Suppose it is X. Now you can check what is the molecular weight for this copper sulfate, and you reduce by 13 so X minus X 13%. So what is coming Y? This Y species, you will see that this is not the CuO, it is actually Cu2. So from here you can see that whatever that is process, that is one process SO2 and this one. So here this is very like steep. So here you are not finding that your that CuO. Ultimately you are finding here this table which is Cu2. So I think it has explained nicely about all about what is happening in the copper sulfate 5 water molecule. So you can easily find out. So if anyone has given you a spectra, you can easily find out what are the species farming and how it is farming. You can calculate all those things. So if you get a raw data of this thermogravimetric curve, you can easily calculate what are the species farming over the time. Okay. Now I will go to the question number 7. So choose the correct option given below for the DTA, differential thermal analysis. DTA curve is used as a fingerprint for identification purpose. DTA method is used for determination of phase diagram. DTA method is used for the heat change measurement and decomposition in the various atmosphere, and all of the above is correct. Okay. Okay. Thank you, Sunil. So I think you are absolutely right. So if you have seen the lecture, so there you have already seen that DTA curve is a fingerprint because each molecule has a unique DTA curve for that. So this can be used for the fingerprint. So it's a unique for a particular molecule. And in the phase diagram also, we can find out the different types of, like we can determine the different types of phase in the phase diagram. Here it is. And a heat change and various decomposition can also measured. I have already like shown like what is the decomposition of copper sulfate in pentahydrate. So their heat change also you can. So in the basically all of this is correct in this segment. Now question number 7. What is the correct statement for the thermogravimetric analysis? Thermal decomposition of chemical rise to decrease in mass, multi-step decomposition of chemical species, thermal decomposition of chemical give the rise to increase in the mass. Can anyone tell what is the answer for this? For this question number 8. Okay, Sunil Pawar is it. Okay, anyone has different opinion than Sunil? Okay, so actually the option is D is correct. So we have seen the thermal decomposition of chemicals which give rise to decrease in the mass. So here we can take the copper sulfate pentahydrate example which I have already given here. So here I have told you all the processes happening in the decomposition of copper sulfate in pentahydrate, and we can find out like what is the percentage change in mass, what are the species farming, what is the end product, that is the real product or not. So these things we can find out. This is the give rise to the decrease in mass. This multi-step decomposition of chemical species also, because this has the multi-step decomposition. Like we have also seen the calcium oxalate, magnesium oxalate. So here we have already seen about the multi-step decomposition of the chemical species. So example, you can take calcium oxalate. So here it will form calcium carbonate, calcium carbonate, and then finally calcium oxide. So first it will lose the water molecule, then it will go to the sorry yeah after then it form the calcium oxalate, then it will go to the calcium carbonate, then finally it will form calcium oxide. Correct. So here also the important thing, you are doing under nitrogen or oxygen. If you do under oxygen, it will form CO2. If you do under inert, the CO will evolve. So this is the effect of environment. Now the thermal decomposition of chemical give rise to increase in the mass. This is also, we have seen the iron in the air, that is the one, and we have also seen this FeS2 under oxygen, right? These are the two examples we have seen where the thermal decomposition of chemical give rise to the increase in the mass. So basically here it will form the iron oxide and Fe3O4. Here it will form the ferrous sulfate, Fe2SO4, ferric sulfate. So these two example we have seen, like yesterday I have shown you this, today I have shown this, where the thermal decomposition of chemical give rise to increase in the mass. So ultimately your D option is correct. Now I will go to the question number 9. So fill in the blank with the suitable option given below. The area under a DTA, differential thermal analysis, peak give the measure of heat capacity, enthalpy change or entropy change or free energy change. Can anyone tell? Okay, Sunil is saying B. Okay. Anyone else? I will wait for 15 seconds. If they have anyone says have a different answer. Okay, so basically Sunil is right. So that is the answer is enthalpy change. So I can tell you how. So this is you have delta T and this you have T. Now you have something curve like this or this. So if you integrate delta T by T from T1 to T2, suppose this is T1, this is T2 dt, you basically get M delta H with some constant. These are the conductivity factor and the calibration. Sorry. So these two factor is in the, so basically you are going to get the enthalpy change in this. Now why not heat capacity? So because here we are measuring the difference between the temperature of the reference. You have a reference, you have a sample. So here we are measuring only the temperature difference between sample and reference. So here it not depend on your heat capacity, right? Because there is no term regarding heat capacity in this. But once we do this DSC, differential scanning calorimetry, here we are going to measure the heat, right? So your heat is some kind of, you have M C delta T, right? So this is the capacity. Here you have heat capacity term, right? So there, like in the DSC we have the heat capacity term, but in the DTA we don't have any heat capacity term. So it doesn't depend on the heat capacity of the material. Now free energy change and entropy change, these are two completely different, because entropy change we can't measure the entropy change through this curve in the DTA and the free energy also, that is delta G, because delta G you need to have a delta H minus T delta S. So now you don't know delta S, so how you will calculate your delta G? But you only know the delta H, which is the enthalpy change. And now, so in the DTA curve, we have the what are the process we can see, like glass transition, crystallization, melting, and sublimation. And we have seen also what are the processes which are the exothermic, which are the endothermic. So these things I think you have to go through. Yes. Now, in question number 10, which analytical method is widely used in the pharmaceutical and food industry? Can anyone tell? The differential thermal analysis. Anyone else? Okay, so basically this is the your you are already studying from past 2 week. What is the differential thermal analysis? Oh, uh, Surya is saying C, the electrochemical analysis, calorimetric, and gas chromatography. Now Surya has put a question like why can't it will be C, right? So there is like people use also electrochemical analysis. So because your professor lecture has already discussed that it's widely used in the pharmaceutical and food industry. Because you why this is very important, because once you are going to make any food like compound or pharmaceutical like tablet and all, you have to know the what is the thermal stability, what are the component farming under under decomposition and all. So for that you have to have like definitely use the thermal analysis. But people used to use the electrochemical analysis, calorimetry, and gas chromatography, but not in that frequently, right? Surya, do you agree with me? Like people used to use this electrochemical analysis, but differential thermal analysis like must, because any compound you are farming, you have to know the what is the stability, thermal stability, and what is the decomposition component is farming upon heating. Yeah. So this this is last. So I have already put in the this what are the things there in the lecture. So basically. Um, this influence of heating rate, or like how we have to choose the whether we are going to uh, move the fast, like give the faster heating or slower heating rate. It has given a very nice example which I just wanted to discuss you. So suppose this is the 25 Kelvin per minute. So this is your first graph. So can you see that immediately there is a whatever the transition is there, this transition, you can't see, because so one most thing is there. This is the time, not the temperature. If you go to the temperature, you will know, because here suppose you are going from this one. So if you are going 25 Kelvin per minute, like in a minute you will go to 25 Kelvin. That's how you see. So whatever processes is happening in the small duration, that you will not going to find out. You will end up with a final product. So these small transition you will basically lose, because so suppose this, you are taking this temperature range. So if you are going from here to directly here, you will find out this product and this product, but not the like this transition you will not able to get the notice. So this is the like what is the sample control heating rate. But if you are going to go very slow, it is time consuming. So you have to have optimizer what is the control heating rate, where you can see what are the R processes is happening, and clearly that is our motive. So this crucible, like influence of crucible, so this alumina crucible basically be used to use, it can go around somewhere 1300 on centigrade. We went to sapphire crucible, which are basically more resistance with very high melting point, but which partially dissolve and penetrate ordinary aluminum crucible at high temperature. So for this we have this crucible. Now we can go to the like platinum crucible. It has good thermal conductivity, but you know the platinum is very nice, have very nice catalytic effect, so that can influence your combustion reaction or any reaction, so it may affect. So that's how, like, this is the disadvantage of platinum, but it has advantage, other advantages. So this is the copper sulfate pentahydrate decomposition, which I have already told. This is the sucrose decomposition, so I have already discussed. This is the question. So this is same, like how we are going to, if we get the DTA, how we are going to get the heat and all. So this is the DTA thermal analysis. What is exothermic and endothermic, which I have explained while discussing the assignment. So this is one curve. This is the DTA curve. So this is if it is going in the up direction. So basically it is a, if you are having like this, another is like this. So this is your exothermic, this is endothermic. I have already told, because this is your delta T, which is sample minus reference. So this is the DSC setup. You have already gone through, like how we put the two sample, what are the different component, what are the things we are going to get from this differential um, scanning calorimetry, what are the reaction like melting, solid reaction, polymorphism. This is the all kind of things people has already get from the differential scanning calorimetry. So the principle of operation, what we are going to measure, like heat flow we are going to measure in this, and one heat flow if you are going to measure, so specific heat capacity we must need, that is the difference from your DTA and DSC. So these two types of DSC there, power compensated DSC and heat flux DSC. So these are the things like you have gone through already, how to find out DSC and all. And here this we have seen whether the large well-defined endotherm or we have shallow and broad. So one is like this, another is like this, something like this, broad. So this kind of processes, which process is endothermic, which process is exothermic, whether it is shallow or like large, broad or well defined. These are the thing like you can see in this kind of example. So these are the DSC application. So this have already in the lecture number 14. Say told 1 minute. I think it has reverse it. Minute, right? So this is the DTA instrument, how we used to have a thermocouple connected to voltmeter. So one is placed in the inert material such as alumina, while other is placed in the sun, which we are going to study. So what are the component in this? This is a detailed discussion in the lecture number 14, which I have like put just so you can just go through like what are the, so basically you have to go through what are the working principle, how people are doing, if you are getting a curve, what are the like things we need to keep in mind. So these things like you have to go through. So I think with this I will say thank you to all, and I will stop the recording.